right, so we go from terms to families. Isn't math so warm and cuddly and fuzzy? Yeah, because today we talk about number families. Families that are isolated together in their own little groups based upon their family characteristics. I mean, your book uses the term families, but let's be mathematical. What we're really talking about here are number sets. And a set is anything, any group of something that shares a similar characteristic. And we are going to separate numbers into various families or sets based upon what kind of numbers, what kind of characteristics they show. All right? It's good to be able to identify this belongs to this set and that belongs to that set. And you've heard a lot of these words before. Now we're just going to put them all together and see how these different sets relate to each other. All right? So number sets, all right? There are a number of them, all right? And your book gives you 4, but I'm going to give you all 7 number sets to complete your ability to do math all the way through college, all right? So the first number set we talk about are called counting numbers, all right? Probably the most basic set of math numbers ever devised, because this is when, before they even had math books, people still needed to use numbers to count things. And so if you're counting something, like sheep, for example, you would start with 1, 2, 3, 4, and so forth. And indeed, the set of counting numbers starts at 1 and goes off to infinity, depending on how far you want to count. And that's what these 3 dots are called, ellipses, which means continue the pattern to infinity and beyond. So counting numbers, you notice, are whole numbers. They don't have fractions, they don't have decimals, and they don't include the number 0. Amazingly enough, 0 did not become part of our number system for a very long time. People didn't need a 0, all right? You just kept counting and counting, all right? 0 comes into the second set of numbers called whole numbers, which are exactly the same as counting numbers, except now we've added a 0. And we show sets of numbers by using braces, and if they go on to infinity, we use 3 dots, not 2, not 4, called ellipses, that show continue the pattern on forever. So the only difference between counting numbers and whole numbers is that whole numbers includes a 0. All right? Next, stuff you've been working with for a while now called integers, right? And we can define integers very simply as all whole numbers, right? 0, 1, 2, 3, 4, 5, and their opposites. So that now we can also include negative numbers as well. And so we would show integers as a set with braces, and I've got -4, -3, -2, -1, 0, but that pattern goes off to infinity to the left, and 1, 2, 3, 4, 5, ... goes off to infinity to the right. So in integers we have whole numbers and their opposites. But notice that we don't have any fractions or decimals. All right? Those are not part of the family of numbers called integers. Integers have to be whole. No decimals, no fractions, and so forth. All right? Now, the fourth group is rational numbers. And now we get into the decimals and fractions. We want to be more precise. We need to know what is between 1 and 2. All right? And so we have this group called rational numbers, which is any number that can be formed by a ratio, like 6. You can make 6 as a ratio by saying 6 over 1. 6 divided by 1, 6. 2/3, 2 divided by 3, a ratio, 2 compared to 3. So now we can do fractions. 2/3 is a rational number because the amount of 2/3 can be expressed as a ratio. This also includes decimals, are rational numbers, 3/10, 0.3, even repeating decimals, 0.3 with a bar over it. If it repeats on to go forever, it's still a rational number because 0 with a 3, 0.3 with a bar over it can be expressed as a ratio, 1/3, right? So all repeating decimals can be expressed also as fractions, and as fractions they become a ratio, and that makes them rational numbers. All right? Now, couple of bonus number sets here, all right, that if something's rational, there could also be the opposite of rational numbers, irrational numbers, all right? Irrational numbers cannot be expressed as a fraction or a ratio, all right? Fractional, you know an irrational number when you see it because it is a non-terminating, in other words, it goes on forever, but it doesn't repeat. You know any numbers like that? Eating a piece of pie right now? Yeah. Pi is an example of this type of a number called an irrational number. Pi goes on forever, but it never repeats, all right? And something like the square root of 5 also goes on forever, but never repeats. You get closer and closer to some number, multiply times itself that makes 5, but you never ever get there. And that makes 5 irrational. And we have to treat those numbers much differently than we treat rational numbers. All right? So, yeah, irrationals we get into in 7th and 8th grade. How do you deal with them? All right? And it turns out it's not that big a deal. All right? But in this lesson, they won't talk about irrational numbers. And here's a couple more they won't talk about. All right? The idea of real numbers. All right? It's what you've been working with your entire life. All right? Real numbers are simply anything that can be found on a number line. When you were shading in a number line, you were showing all the real numbers that satisfy that inequality. All right? But it's just that real numbers include integers, fractions, decimals, repeating decimals, but they also include all rational and irrational numbers. You can find pi on a number line. You can put pi on a number line, it works, all right? So these are what are called real numbers, all right? It's what your calculator deals with. It's what our math books deal with, all right? We only work with real numbers. However, you should be aware that there is a family of numbers that are not real. These are called imaginary numbers. And they cannot be found on a number line. And they cannot be found on your calculator either. You want to prove it? Try punching in the square root of -4 and see what your calculator tells you. Chances are your calculator will say something like domain error, number error, whatever. Well, domain is simply the math expression that says all acceptable values, all right? Your calculator can only deal with real numbers. The square root of -4 is an imaginary number. It doesn't exist in nature, all right? And you have to deal with them, obviously, a whole lot different than you deal with real numbers. But amazingly enough, imaginary numbers do come in handy in many, many applications as you get higher and higher up into math. They don't just, they're not fairy tales that are nice little stories, but they actually have some utility. But it's going to take a huge background before you start to understand how to deal with imaginary numbers. But once you get to imaginary numbers, that's about it as far as number families go. All right? So how do we put all this together? How do we show this? All right? Well, we can show family relationships with sets and things called subsets. All right? You've got a big circle here and a small circle inside. All right? We see that this small circle is called a subset of the bigger circle. Why? Because every single thing in this little circle is included also in the big circle. But not everything in the big circle can be found in the little circle. So the little circle here is considered a subset of the bigger circle. All right? And we can use this idea of big circles, smaller circles, what goes in one but isn't in another, to show the relationship between all these numbers. This is one of the key things you're going to need to get in your notes here. All right? Start off with a big circle the size of your notebook paper. All right? Make it nice and big. That big circle are all the real numbers that we deal with. That includes everything you can find on a number line. And notice that all these other circles are combined inside of real numbers. But there's one little blob that is not at all a real number, and that's over here on the side. That's imaginary numbers, all right? They have no part with real numbers. They're a totally separate thing. Nothing in the imaginary group is also in the real group. They're different, all right? But we see here that in real numbers, we've got this subset of irrational numbers here, all right? All these irrational numbers, the square root of 11, all right, is an irrational number. It is a real number. All irrational numbers, we can say, are real numbers. Why? Because every single thing you find in the irrational circle is also found in the real circle. So we could say that irrational numbers are a subset of real numbers. All these other circles are also all found in real numbers, so they are all subsets of real numbers. We get a bigger circle here, now we talk about rational numbers, anything that can be expressed as a ratio. Then inside of that circle, you've got integers. Inside of integers, you've got whole numbers, and inside of whole numbers, you've got counting numbers. All right? So you can use this to answer questions like you'll see on tests and homework that say, are all counting numbers whole numbers? Yes or no? Well, we look at the counting number circle, and we see that every single counting number, every single number that is considered counting inside this circle is also part of whole numbers. So we can say all counting numbers are also whole numbers, all right? Can we say that all integers are also whole numbers? All integers are also whole numbers. Well, we look at the integers and we see a whole bunch of integers here that are not part of whole numbers. So the answer there is no, not true. All integers are not whole numbers. But on the other hand, we can say that all whole numbers are integers. Because all whole numbers, this whole circle, is all included in the integer circle. And we could go on like this all the time. I mean, we can say, are all integers rational numbers? And you would say, yeah, all integers are rational numbers. But are all rational numbers integers? Are all rational numbers integers? No, they're not. Because I've got some rational numbers out here that do not include themselves inside the rational number, or the integer number circle. All right? So we can talk about, are all of these part of these and so forth. We can say, are all whole numbers real numbers? Yeah. Are all counting numbers a subset of integers? Yes, because all counting numbers are also found in the integer circle, all right? The idea is if you can find one number that is not part of the circle, like if it said, are all whole numbers rational numbers? Well, you can pick a rational number like 1/2, and that's not a whole number, so you can't say all whole numbers are rational. But you can say all whole numbers are rational numbers, but not all rational numbers are whole numbers. And that's why you need a chart like this to keep it all together. If everything in that is also found in the bigger circle, then yes, it's a subset. It's part of it. But if there's space that isn't part of it, then whole numbers, all whole numbers are not counting numbers. And remember, the only difference between whole and counting is whole has a 0 and counting doesn't. All right? All right? Another way we can show number relationships is using a number line. And you've been doing this already without even knowing it, because everything on this number line is a real number. No matter where you put a dot, you've hit a real number. Both positive, negative, 0, fractions, decimals, irrationals, rationals. It's a real number if it's on the number line, all right? But others would be shown differently, right? We wanted to show the whole numbers on a number line. Well, I could put a dot on each whole number, right? And I've got a second arrow showing that continue these dots forever in this direction, but not in that direction. But notice I don't shade, I don't squiggle things in here, because that would say that 3.5 right here is a whole number. It's not. You can't just shade in stuff anymore if you're asked to display just whole numbers. If I want integers on the number line, I can't just shade it all in because that would include fractions and decimals, and integers don't. So I have to very carefully make dots on all the integers and then show an arrow going to the left and an arrow going to the right to show that pattern continues forever. But this is a point where I would not be shading in the number line. Alright? So you would see something like, show all counting numbers more than 2. Well, first of all, you got to figure out, where does my first dot go? Can I put a dot on 2? Is 2 more than 2? The answer is no. So the first counting number more than 2 is right here, 3. So I put it, and this is not where I do shading, because remember, if I shade, that says 3.5, 3.6, and so forth. All right? So I can only put dots on counting numbers, and then a nice big fat arrow to show that that dots continue for longer. All right? Yeah, so be careful with the shading now. This is different than, x is greater than 2, right? If I wanted all numbers greater than 2, which is what this says, then yeah, I'm going to have an open circle on 2, and I'm going to be shading in that direction, because 2.5 is greater than 2, all right? Pi is greater than 2. But that's not what this says. So be careful and use dots when you need to. All right, with that under your belt, that takes care of lesson 86. Do A to D and 9 to 10, and we'll see you later.